First of all, I have to say a lot of thanks to Wouter, to Franz, particularly also to Marcel, and most of all my compliments to our host here, to Dimitris. Thank you very much that we can stay here to have some discussion about very important questions. We heard different positions this morning and also with the beginning of this afternoon, and I'm not sure I can reduce this gap in these positions or even close this gap. But I try to give some maybe additional aspects which help to relativize a bit. So, is what we are faced in Germany and in many other countries that we are asked, what have you done today to protect climate? And not the Greece so much, but the Germans and also the Nordic countries. I'm a little bit a representative by the journal Science of Climate Change, also for the Nordic countries, therefore I mention this. They tremble, yeah, but so my answer to this question is I try to understand better science and to search for the truth. And let me continue with this sketch here. I think this invitation here, this workshop, well contributes to go along the scientific pathway, even though we have some smaller different traces here along, which hopefully are matching and coming together at the end. So that was my introduction to this point. I want briefly give a summary of the IPCC's explanation of increasing CO2 to better show the difference to my own approach to understand the carbon cycle. So, okay. Despite the dramatic temperature and CO2 changes over the Paleozoic, that means over the last 540 million years, with the inception of the industrial era, and particularly, not only for many climates, particularly for the IPCC, natural impacts no longer exist. We have this position here also, only humans are responsible for everything. Instead, they claim only fossil fuel emissions are responsible for the increasing CO2 concentration in the atmosphere. And second important point, almost all of the temperature increase is caused by the greenhouse effect and particularly by CO2. Today, I'll concentrate only to this first claim, of course. So we saw different pictures and numbers already in the morning and now about the balance of CO2 in the atmosphere and other reservoirs, only to have a small summary and to make you familiar with my idea I want to present. So before 1850, carbon cycle was in balance. We heard this several times with a concentration of 280 ppm. And an emission of about, and also absorption to make this in balance, of 80 ppm per year. So over the industrial era, the IPCC claims this has come out of balance with nowadays about 410 ppm over the last 10 years. This is the number we find in AR6. And we have additional emissions and also absorption in this almost stable behavior of 26 ppm per year. So the human emissions, we heard this number too, are about 4.8% in numbers here in ppm, 5.1 ppm per year. Again, the average over the last times. From these are directly absorbed about 54%, and the rest, 46%, airborne fraction. So altogether, CO2 increases from 280 to 410 ppm, and only due to the human emissions. The removal time, some people call this adjustment time, is assumed to be up to 100,000 years. And the residence time, also mentioned a lot of times, is the ratio of 400, the content of CO2, divided by the in or out fluxes, around 3.8 years. So this as a remembrance of some pictures. This sketch shows this again. Look, we have 130 ppm here with a residence time after this model of 3.8 years. And part of this staying in the atmosphere for up to or more than 100,000 years. On the other hand, we have an influx here. The anthropogenic emissions, 50% or more are directly absorbed, and the other part is emitted to the atmosphere and stays there. So when we balance this in simple words, as a balance equation here, the emission rate minus the absorption, which goes here to the external reservoir, gives the airborne fraction times the emission rate, the anthropogenic emission rate. And this indeed fits very well. When we look to this graph, this red or magenta graph here, this fits very well with the Mauna Loa curve. Yeah, for a constant airborne fraction of 45.6%. So, but what a logic, I say. There are some basic problems with such an approach. So, first, it is assumed a constant natural cycle of 280 ppm and neglects all additional native emissions we can observe. This is in contradiction to paleoclimatic and also the actual observations. 54% are directly absorbed, but no uptake of the previous content, the 26 ppm, which are oscillating all the time in the atmosphere. Yeah? This is, from my understanding, violation of the equivalence principle. Then we have a point that the absorption is proportional to the emission, not to the concentration. We saw this from the balance, and we see this also in a more advanced the Bern model. That's the same situation. Yeah? This is a descent to native decay processes and the observation of the C14 decay. Total CO2 content in the atmosphere is exchanged within about 4 years, assumed by IPCC as an inert gas without real absorption at the surface or the external reservoirs, only circulating around. Yeah? This is no real absorption and emission. Even we have different compounds of CO2 in the oceans and in plants in the biosphere. So, and the more elaborate Bern model considers even 5 different absorption channels with different adjustment times. There is no reason to understand these different adjustment times, which are again proportional to the emission. And even worse, they are working in series, like a cascade, not parallel. when we are talking about different reservoirs, yeah, the biosphere or the oceans or something else more, yeah, who is familiar with some lifetime discussion in atomic physics and nuclear physics, also here in this case, knows that different channels are developing parallel. And so 1 over tau 1 plus 1 over tau 2 plus gives as a sum 1 over tau, as you were mentioning this too. This is well known, very long. So there is no reason to assume different decays and in this way working in series. So these are only a few comments to this. There is also some modified IPCC interpretation, which favors Ferdinand, Corley, and some others. And there I reduce it to some simple basics, where we see that here we have a natural emission in pre-industrial times of 280 ppm. And we have for this assumed, better than the previous model, now in absorption proportional to the concentration. But here is only used the concentration of the native molecules of native origin or native sources, even when they are mixing of native sources. So, and with the absorption or with the residence time for these native molecules of 3.5 years, this exactly cancels. So this equation is nothing else than an equation, a balance only for the anthropogenic emissions and their absorption. Now discussing the excess concentration, the difference of the actual concentration minus the native concentration at 1850 or 1750, almost the same, and introducing a new time scale, a new time constant, tau A. Some people call this adjustment time or differentiate this in different adjustment times. But in reality, it is nothing else than a residence time, a second residence time, only for the anthropogenically increased molecules. This violates again the equivalence principle, and in my terms, to separate this and to exclude native circulation, this is nothing more than circular reasoning. And last comment, this the embezzled native emissions, which we expect over the industrial area and also in previous times, a lot going up and down, yeah, in the emission rates, as we saw in over the last 800,000 or even more years. So these to exclude these, to embezzle these native emissions, to compensate for this, it is necessary to introduce another time scale, a time scale with tau A. And when you are using for this time scale 50 years or about this, then you get this red graph here again, yeah, which fits very well in average with the Mauna Loa curve, and here with the airborne fraction. So from this you see there are different reasons for a more realistic approach in agreement with all observations and physical causalities. These studies I'm presenting, particularly the last years since 2020, arose from a close cooperation with the late Murray Selby from Macquarie University, Sydney. I want to repeat about his very dramatic period and life, and how he was disqualified from his university. We concentrate here on the atmospheric physics. Our approach was and is to include temperature-dependent natural emissions. I call here En as a function of temperature and time, and anthropogenic emissions, of course, as Ea over the industrial era. The absorption rate, as already discussed in this modified model, is assumed, is good reasons, is proportional to the CO2 concentration, but not the excess concentration, the difference to 220 ppm at 1850, but the total CO2 concentration we have. When this total CO2 concentration, there is no absolute barrier, some limit for this. When some processes in emissions are reducing, also the concentration goes below 280 ppm, of course. So the absorption rate is this ratio of the actual CO2 concentration divided by effective absorption time, we call this. I explain this in a moment, not to confuse you with additional terminology, but this is close to the residence time, of course. This gives the well-known conservation law in mass, or also for the concentrations in the atmosphere, the changes in CO2 as the sum of the emissions, anthropogenic and native emissions, minus the uptake. So, in this way, nothing more. And to a good confirmation for this balance equation, and also to understand a little bit more details of the absorption process in the atmosphere or the extraneous reservoirs, it is good to look to the radiocarbon as a tracer of the carbon cycle. In the stratosphere, from the incoming cosmic radiation, neutrons are colliding with nucleus of nitrogen in this way and kick out a proton, and after a very short time we have some oxidation, and in this way is formed the C14O2 as an isotope lock, we call this. Now, this is only in a concentration of about 10 to the minus 10% compared to the stable isotope locks. The radioactive lifetime already mentioned, I can go quickly about this, is much longer than any observation time we are interested in. So, due to the bomb tests up to 1963, this concentration was doubled, which was in some sense afterwards some luck for the study of the atmosphere, the uptake. And from this we know that the mostly plotted and discussed is the difference of the CO2 concentration in the atmosphere relative to a reference, normalized to this reference, and times 1,000 to present it in per mil. So this gives the balance equation, and we can check this. Here is a measurement from Vermont in Switzerland, and we see on first glance, we have to check this in more detail, this is an exponential decay with fast oscillations, which are due to the Brewer-Dobson oscillation, and particularly in boreal winters, we have some injection into the troposphere, from the stratosphere to the troposphere. This is a balance for considering the stratosphere, the troposphere, and the surface as a 3-volume system. Yeah, it is even extended to a 4th volume with a decay rate from the surface to the lower ocean, whatever. The full balance equation for the masses is shown here. As you see, some different processes. This is the injection of the C14, the creation of C14. This goes via some decay processes to the troposphere, and from the troposphere to the surface, and from the surface even can relax to the deep oceans. So when we consider this as a mass balance, we have to consider that masses are not equal to concentrations. They are strongly dependent on the concentration, on the total masses in the stratosphere, the troposphere, and in the surface. So this only as a comment. And coming back now, when we calculate this for this 3-volume system, we get the anomalous concentrations C14 from the stratosphere, the blue graph for the troposphere, and the red for the surface. So, and we see with very fast, the fast oscillations needs in absorption time, which is shorter, let me say only shorter than 1 year, about 8 months, not more. This is the direct absorption. We have the direct absorption time. But due to this absorption in the surface, some molecules are accumulating and they can be re-emitted to the other reservoir, up to back to the troposphere. So this is a re-emission process which has to be considered, and this gives then the effective absorption time. We see this here fits quite well for the troposphere with the decay, which we plotted here as a dashed graph, with about 8 years. There are some differences to other plots. Looking at the southern hemisphere, I don't know the real differences, but here from these graphs here, from Vermont on the northern hemisphere, we get these results here. So, and this is only this balance equation system only for the troposphere, as briefly shown here, that the concentration in the surface is increasing. When this is increasing, this is a re-emission term for the concentration in the troposphere. This is the decay process, this is the absorption, this is the re-emission. So, and we can, as some first approximation, approximate this by the concentration of the troposphere, and then express this as a ratio, which we call here beta. And then we get this kind simplified equation proportional to the concentration in the troposphere divided by an effective absorption time. This effective absorption time from this decay here is maximum 8 years, but it can also be shorter, as we will see. So, and this means this beta can go up to 0.9. Now, when we transfer this also to the anthropogenic emissions, this was only the discussion for C14. When we transfer this also to the anthropogenic emissions, then we see that with increasing emission due to the CDIAC data here, the gap between the troposphere and the surface is even increasing, which means due to this direct emission into the troposphere with the anthropogenic emissions, we can get even an effective absorption time faster than C14. This is due to this increasing difference, and this inhibits a larger offset of the direct absorption time by re-emission. That is the reason. And the effective absorption time can, as an upper limit, can we explain when you have red molecules and you have blue molecules, and they have a ratio of red 5% to the blue, then also the mixing in the atmosphere cannot be more than 5%. So this is the upper limit, and which gives here 4.8% at the moment with the emissions, about 20 ppm with the actual concentration of 420 ppm. Okay, and when we look to 23, these calculations show us that the concentration is only about 13 ppm with such an effective lifetime or better absorption time. This is 9% of the increase of the industrial era. But in average, a limit should be this here. Okay, how do we explain these data and the larger increase of CO2 over recent decades? So we know that the absorption and also particularly the emission depends intrinsically upon temperature. This is documented in all these different seasons. And let me see only this year. The seasonal emissions and uptake are almost 6 times larger than the anthropogenic emissions we have. So, and they are absorbed and re-emitted over the next season and so on. There is a strong influence due to these cycles. The soil respiration even increasing exponentially with the temperature, or the emission and uptake by the oceans. And different to the IPCC, we don't ignore any temperature-dependent processes, not in the biosphere, not in the oceans, and permafrost. Only last comment, 1 million submarine volcanoes are expected, and about thousands of them are active. Why there should be no natural emission? I ask you, how can you imagine that this is the same 1850 like nowadays? No change. When this is right with these longer integration times and accumulating in the atmosphere, this has to sum up to infinity. But we have a decay process, and when this is a fast decay, the faster, the smaller the perturbations are found. Okay. We look to, as a reference, to the Mauna Loa curve, and we see the obvious seasonal modulation, which are similar from one year to the next. There comes up the question, which additional emissions we are expecting when we look to this curve. We look to the derivative of the deseasonalized concentration. I call this C prime CO2. And so sum of the emissions minus uptake gives now the net emission, the difference. And we look to this net emission. Here, this is the net emission we find when looking not only to these integrated diagrams of the Mauna Loa, but more closely. Everyone can go to this data and look and find these oscillations which are determined, which are really with sharp peaks, which coincide with the El Niño events and other special events. And we have an increase here of about 2 ppm per year over 65 years. This is less than the anthropogenic emissions, with about 3 ppm per year as an average over the last years. But the net emission rate is the difference of the actual emissions minus the uptake. Yeah, therefore, it is increasing slightly. And when we have a fast uptake and a short residence time, then this is also increasing less rapidly. So, finally, we look to the temperature data. And let me make clear, over mid and high latitudes, there is not real dramatic temperature increase, but different to the tropic areas. Particularly in the tropics, we have a continuous increase over land and sea, well represented by the sea surface temperature anomaly, with spikes which coincide with the El Niños. These are spikes here and here and here in distances of 2 to 7 years, most of them. This is a good reason to check if this temperature increase fits with the emissions as the derivative of the observed CO2 concentration. So, here is again shown this emission rates at Mauna Loa, and I should make clear that generally the emissions over sea and land we are discussing, but the outgassing of the oceans, this was mentioned by Ferdinand and others, is relatively small. This is depending more strongly on wind and changes and other effects, the waves, but the temperature impact is relatively small, only 3% per degree centigrade. Much higher is the temperature response of the soil respiration, and particularly in tropical areas. And when we look to this data, which is more than 10 times the sensitivity than for the oceans, we can compare this and calculate this with this emission rate. And look, when we compare this to each other, this is our correlation, which is about 80% between the measured emission rates and the calculated emission rates using this temperature graph. So, and let me make an important note which goes back to our different discussions, hence or X and whatever, yeah, the emission is in phase with the temperature. This we see here, the emission, we have the blue graph with the temperature. There is only a very small delay. We are looking here on a much larger time scale. So the concentration has a phase delay
of 90 degrees
to the temperature and also to the emission. Only the concentration can go up when there was an emission change. Yeah. So first the change of the emissions proportional to the temperature, and then the response increase of the CO2 concentration in the atmosphere. This goes back to early studies in the 2030s by Humlum, Stordal and Solheim, and also Murray Selby, and of course the latest paper from Dimitris. So CO2 cannot be the reason for temperature increase, at least not for this increase we see here. Finally, we can compare this with the direct measurements at Mauna Loa. That means what I just was calculating for the emissions, we again have to integrate the theoretical emissions. We have to integrate here as the net contribution as a function of temperature and time, and the anthropogenic emissions. And all this together gives the observations, or compared to the observations. You see, this is a calculation which fits almost exactly with the measurements, which covers almost completely the measurement. And the green curve only represents the natural part, the native emissions, including the seasonal modulations. So, what we see, the anthropogenic contribution in these calculations contributes 13 ppm, which is 9% of the increase since 1850 in the CO2 concentration, not more. And we also see the anthropogenic emissions here as the lower graph, maximum 5.1 ppm per year, which is 4.8%. And when this emission is stabilized, no longer changing, over the next 20, 30 years, we come to an equilibrium, expected equilibrium within about 10 to 15 years, with an additional increase of not more than 10 ppm, only under the conditions of stable emission over the next time. Okay, finally, only one comment about the back data which were mentioned here earlier, and I don't have to repeat this in detail. So these measurements going back to chemical analysis and not to proxy data, and which show this black curve, and with the same procedure and temperature response I explained with respiration and all the other things. Applying this also for this period here and using the SSTA or the data of Colony, and soon we get this red graph, which reproduces not the peak absolutely, but in principle very well, this increasing CO2 concentration around the 40s, and also the further increase we have here, we observe here. So finally, let me say, carbon is controlled by a first-order absorption process acting equivalently for native and anthropogenic emissions. The effective absorption time cannot be longer than 10 years. We also have information about this from a different study, only considering the seasonal emissions, which gives the same number, maximum 10 years, but it can be shorter, as I tried to explain, due to this special behavior, shorter than 1 year or 1 year. With anthropogenically caused CO2 less than 10% and global warming over industrial area by about 0.3 centigrades, which results from own calculations, and by the way, with a negative feedback, which is determined particularly by evaporation feedback. So, and then we see humans are responsible for a global warming of 300 centigrade, not more. To further reduce this absolutely negligible contribution, we endanger a secure energy supply, and with this, a prospering economy and stable standard of living. Thank you for your attention.
Okay, thank you very much, Herman. I gave you much more time, so I hope you enjoyed it.
You didn't say anything.
No, I didn't say anything because I found it important that you could finish just like you did.
To the troposphere.